Welcome to Kako Education Services. We thank you very much for subscribing with us, and if you have not done so, please do and share with your friends on this audio and videos that we shall be sending. Our topic today is states of matter. We all know the states of matter, that is gases, liquids, and solids. All these states of matter have got specific characteristics. To begin with, we have gases. We know that gases have no fixed shape or volume. Their particles are far apart from each other, and therefore they can be compressed. Their particles are also randomly pressed. Then their particles can also move freely from one space to space, from place to place, in all directions. Those are the properties of gases. Liquids. Liquids take up the shape of the container in which they occupy. Liquid particles are close to each other, and we all know that liquids have a fixed volume. They can be slightly compressed. Their particles are fairly random, and then they have limited movement between them due to the spaces. Solids have a fixed shape and volume. Their particles touch each other, and therefore they cannot be compressed. Then also, there are usually regular arrangements within their particles, and then due to the fact that they touch each other, they do not change positions. We only just have simple vibrations amongst the particles. So those are some of the properties of states of matter. Now, the state of a substance at room temperature and pressure will always depend on its structure and bonding, the type of bonding that exists within that state. For example, if you look at a substance like carbon dioxide, which is also a compound, at room temperature, it exists as a gas. When you look at the structure of carbon dioxide, it is usually known as the simple molecular structure. And the type of bonding, we always have van der Waals forces of attraction between these atoms. Then look at a substance like silicon 4 oxide. We know that silicon 4 oxide has a giant molecular structure, and the type of bonding is the covalent bonding. So all the states of substances in nature, in most cases, they take up, they will have structures and bonding determining their states. Now let's take an insight more in the gaseous state. And our key points in the gaseous state, we are going to talk about the kinetic theory of gases, ideal gases, the general gas equation and how it can be generated, using the general gas equations to carry out calculations, and also relative molecular mass. Kinetic theory of gases. This theory rotates on the idea that molecules in gases are always in constant movement. I repeat that. Molecules in gases are always in constant movement. And it makes certain assumptions for us to verify the theory, whereby the first assumption says that the gas molecules move randomly and rapidly. they move randomly and rapidly. Then the second assumption is that the distance between the gas molecules is much greater than the diameter of the molecules, which therefore makes the volume of these molecules negligible. There are no forces of attraction or repulsion between these molecules. That is the third assumption. We do not look at the forces of attraction, neither do we consider the repulsion between these molecules. The fourth assumption is that all collisions between the particles are elastic, and this means that there is no kinetic energy that is lost in collision. We all know that when collision takes place between two particles, some energy is lost. But for us to look at the kinetic theory of gases, we have to make another assumption which says that there is no kinetic energy that is lost when collision takes place between two particles or two molecules. The last assumption we are making here is that temperature of a gas is related to the average kinetic energy of molecules. When you increase the temperature of a gas, you increase the kinetic energy of the moving molecules or the moving particles. Therefore, that's why we have to consider this assumption whereby the temperature of a gas is going to be related to the average kinetic energy of these molecules. From all these assumptions, theoretically, they fit a certain specific gas, and that is an ideal gas. It is the only one that can fit within the description that you have given above or in the assumptions. In real sense or in reality, the gases that we do encounter most of the times do not exactly fit our description. And usually we call these gases real gases. For example, carbon dioxide, nitrogen, oxygen. All these are real gases. We also have to take into account that some noble gases that have small atoms, such as helium and neon, tend to approach the ideal gas behavior, and they are favored by the intermolecular forces, which are very small, and that's why they tend towards or they approach the ideal gas behavior. So the gases that obey all the above assumptions, like I had earlier said, they are ideal gases. That is, they have no intermolecular forces of attraction between them. Their volumes are negligible. At collision, there is no kinetic energy that is lost. And we are going to use the ideal gases to generate the general gas equation. So for us to come up with this equation, we have to look at the following things. We have to look at how the volume of gas changes with pressure and temperature. It's important that we take note of the following: that the volume that a gas occupies depends on its pressure, which is measured in pascals, and its temperature, that is always measured in kelvins. If you have temperature that is given in Celsius, this has to be converted to kelvins. For example, if I have 100 degrees Celsius, to convert them to kelvins, I'll get this 100 plus 273, which will give me a total of 373 kelvins. And that conversion is done. If we have a gas that is enclosed in a container, this gas will always exert a certain pressure on the wall of the container. And this is because the gas molecules are constantly hitting the walls of the container. If we decrease the volume of this gas at constant temperature, I repeat that, if we decrease the volume of this gas at constant temperature, the molecules are going to be squashed closer, or they are going to be squeezed closer to each other, and they will hit the walls of the container more often. They will hit the walls of the container more often. Therefore, the pressure of the gas increases. If we plot a graph of volume against the reciprocal of pressure, this gives us a proportional relationship by a straight line. And we can say that volume of a gas is inversely proportional to the pressure. Volume of a gas is inversely proportional to the pressure, not 1. Then, if the gas that has been enclosed in a container is heated at constant pressure, its volume increases. Its volume increases. And this is because particles move faster and hit the walls of the container with a greater force. If the pressure is said to be constant, the molecules must get further apart. Therefore, the volume of a gas at constant pressure is proportional to its temperature, and this temperature is always measured in Kelvin. Note number 2. From this, we can say that the volume of a gas increases with increase in temperature at constant pressure. To conclude the above notes, an ideal gas will have a volume that varies exactly in proportion to its temperature and exactly in inverse proportion to its pressure. We also have to take into consideration that the volume of a gas is proportional to the number of moles present, and that is note number 3. So combining all the note 1, note 2, and note 3, the general gas equation, if we combine our notes, note 1, note 2, note 3. From note 1, we saw that the volume is inversely proportional to pressure. And this can be written as V, which stands for volume, equals constant divided by pressure. From note 2, we saw that volume is directly proportional to temperature. This can be written as V equals to K temperature, or to KT. Then from note 3, we have that volume equals to constant times number of moles. That is, volume is proportional to the number of moles, and this number of moles can be represented by N. If we combine the above, we come up with an equation which is volume equals to a constant NT divided by P. If we take P on the other side, we can write our equation as PV equals to KNT. If we replace K by R, that stands for the gas constant, we can have our general gas equation as PV equals RNT. I repeat that. PV equals RNT. P, which is pressure, is in pascals. Volume of a gas is in cubic meters. Number of moles, which is N. R, gas constant, which has a value of 8.31 joules per Kelvin per mole. Temperature, which is T, and it is in Kelvin. The number of moles of a gas can be calculated if we are given the mass of that gas and its relative molecular mass. That is to say, N equals small m divided by capital M R, small r. If we get this and we substitute the N in our general gas equation, we can have PV equals small m RT over capital M R. And we can use this equation to calculate for given mass of a gas. You can even use it to calculate for the relative molecular mass of that gas. So let's work out one example. You can write, calculate the volume occupied by 0.5 moles of carbon dioxide at a pressure of 150 kilopascals and a temperature of 19 degrees Celsius. In brackets we have R, which is equal to 8.31 joules per Kelvin per mole. From the above question, we have been given pressure, we have been given temperature, we have been given the gas constant. So our task is to calculate the volume. So the first step is to change pressure and temperature to their correct units. Our pressure is supposed to be in pascals. Therefore, we change the kilopascals to pascals. So if you have 150 kilopascals, to change them to pascals, you multiply by 1000, and therefore we shall have 150,000 pascals. The temperature, we have 19 degrees Celsius. This can be converted to Kelvin by adding 273, and we shall have our 292 kelvins. After converting to the correct units, then we got our general gas equation, which is given by PV equals nRT. If we rearrange this, we can have volume equals nRT divided by pressure. Substituting in our general gas equation, we can have volume equals to 0.50 moles times 8.31 times 292. The whole of this is divided by 150,000 pascals. And we shall have our volume as 8.09 times 10 exponent negative 3 cubic meters as our answer. The general gas equation can also be used to calculate the relative molecular masses of volatile liquids. These volatile liquids are injected in a gas syringe and then placed in a syringe oven where they are vaporized, and we record the volume after vaporization, the temperature under which the liquid vaporizes, and its pressure. And then we can use these values to calculate for the relative molecular mass. So let's try out this question, and you can give us the answer in our comment box, and we shall give you feedback. The question is, when 0.08 grams of a liquid X was vaporized at 100 degrees Celsius, 23 cubic centimeters of vapor was formed. The atmospheric pressure was 1.02 times 10 exponent 5 pascals. Calculate the relative molecular mass of liquid X. In brackets we have R equals to 8.3 joules per mole per Kelvin. Also we have that PV equals small m RT over capital MR. Thank you. Try out. So finally, let's look at the limitations of ideal gas laws. That is where the real gases do not behave like ideal gases. We earlier said that for ideal gases, the intermolecular forces of attraction are negligible, or they do not have intermolecular forces of attraction between them. And the other point, which is key, is that we ignore the volume of the molecules. For real gases, however, they do not obey the kinetic theory in these two ways. The first way is that there is not zero attraction between the molecules, which implies that their molecules have attractions between each other, and therefore you cannot nullify or rule out the attraction between the molecules. Number two is that we cannot ignore the volume of the molecules themselves. These molecules occupy a certain volume, and therefore this must be considered. And these are the only ways in which the real gases deviate from ideal gas behavior. Now, for these differences to be noticed or to be very seen, they are only seen at high pressures and very low temperatures. The deviation from ideality or from ideal gas behavior is noticed under high pressures and very low temperatures. So under these conditions, number one is that the molecules are closer to each other. When you have high pressures and very low temperatures, these molecules are closer to each other. Point number two is that the volume of the molecules is not negligible compared to the volume of the container. Under these high pressures and very low, you'll find that their volumes are higher, and therefore they cannot be negligible. You cannot rule them out. Then, at the same time, under these conditions, there are van der Waals forces of attractions. exist, or we can say that there are van der Waals forces of attractions between the molecules. And these attractive forces pull molecules towards each other and away from the wall of the container. So, if the molecules are pulled away from the container, it implies that their pressure is going to reduce. Therefore, point number 4 is that the pressure that is exerted is lower for an expected ideal gas. The pressure that is going to be exerted is going to be lower as expected for ideal gases. Finally, is that the effective volume of a gas is smaller than expected for the ideal gases. The effective volume of these gases is going to be smaller than expected for the ideal gases. These are the only possible ways under which real gases can deviate from the general ideal gas laws. We thank you very much for paying attention to this audio. Give us any feedback or any clarity that you would want in our comment box. Share with your friends and subscribe. Ask any questions where necessary for clarity, because our major focus is to make sure that you succeed, because your success is our pride. We wish you all the best and God's blessings